Hi. So, as you've noticed, my slides are rather dark. You had the bright side of things before, and now we're falling back in the dark side. You'll see why in a few minutes. I'm Jean-Marc Leroux. I'm the CEO and co-founder of a French startup called Iris, which is here in Paris, just at the other end of Paris. I'd like to thank David, of course, and all the guys from Microsoft who invited us to showcase Minko today. This is a very special day for us because we released the first beta of our new Minko 3 engine. So everything I'm showing today is brand new, and it's available on GitHub. I'll get back to this in a few minutes. First, I'd like to talk about WebGL France. It's the French meetup for WebGL. So if you're interested in 3D, you should join. This is something we've created with the good folks from Sketchfab. Maybe you know about Sketchfab. Anyway, if you're interested in WebGL in general and in web gaming, I think you should join. And we should have our first meetup pretty soon. This is a very new thing, but we already are at 30 or 40 people. So just please follow us on Twitter and join us. So today I'm going to talk about Minko. So Iris is the name of the company, and Minko is the name of the product. So first I'd like to talk about our motivations, of course. I started working on 3D engines 8 years ago when HTML5 was not really an option. And I wanted to build web games using 3D graphics. And there wasn't much at the time, so I started working on a software, a 3D renderer using Flash 8 years ago. Ooh, Flash. It was 8 years ago. And my philosophy has always been to be very pragmatic as a developer. When I create a game, not a web game, not a mobile game, I create an experience. And I think that's very important today when you create a game to have a strategy on how to market it, how to make a revenue out of it. Maybe not have money, just community love, but to be able to make revenue out of it. And so being able to publish your game on all platforms has always been one of my great dreams. And that's the spirit behind Minko. It's a set of tools to create 3D games, not just for the web, but for whole devices. And I'll talk about that today. Then I'll talk about how you create a game using Minko. First, I'd like to present what's inside Minko, because we have three things. The first one, the very simple one, I'd like to say, it's called Minko Enterprise. It's like Dropbox. I'm sure you all know Dropbox. It's Dropbox for 3D files. So when you're game developers, it's a very cool tool to be able to collaborate using your 3D files. So it's a cloud-hosted platform. And what we bring are, for the web, 3D compression and streaming algorithms, so we can load 3D graphics up to 200 times. That's not what I'm going to talk about today. Minko Studio, it's an application you install on Mac and Windows. It's a 3D editor to build 3D worlds. So you create your 3D assets and 2D assets with tools like 3ds Max and Photoshop, but then you have to actually build 3D scenes for your game to integrate things so they can be used in an interactive applications. And that's what you can do inside Minko Studio. So I will show you a little demo afterward, and you'll see it's much easier to create a game when you have these kind of tools. And finally, and I think that's the thing you're going to love the most, and that's what we just released today, the Minko engine, which is a 3D engine and much more to develop applications and deploy them everywhere. When I mean everywhere, it's Windows, Mac, Linux, iOS, Android, and HTML5. All from a single source code. Develop once, deploy on all those platforms without changing a single line of code. Thanks to Minko, you have the power of native with the reach of the web. So you create native code, you write native code, you have the performances of native, and you can deploy on the web. And finally, last but not least, it's fully open source, and it's free even for commercial projects. Okay, so do whatever you want with it, it's MIT. Today, we're already working with a few gaming partners like Ubisoft, which is French, Bigpoint, which is German, and Chilingo, which is EA, basically, so it's American, I guess. And Bigpoint is about to release a pretty big game for Facebook using our engine, so stay tuned. It's really, really a cool work they're doing. So why? Why would you build a WebGL game using C++? because that's actually something weird to do. The thing is that 3D apps tend to be more complex on all levels. Usually, building a 3D application is doing a bigger project because you need a bigger team, you have bigger expectations, you need 3D artists, and it's not just about 50% more D. It's actually a lot more than that in terms of problems and complexifications of your work. C++ is more expressive. It's a given. It's also more complex. I'll show you why today you can do with C++ what you would expect to do with JavaScript in terms of simplicity. So just wait a few slides, and I think you'll be surprised. And our goal is to be able to reuse the past 4 decades, so 40 years of C and C++ code lying around the web for free and open source. So not reinvent the wheel every time, but leverage everything that already exists. So 3D apps also require more performances. You usually have to do through GPU programming, 3D math, 3D physics, as it was demonstrated before, artificial intelligence, massive files loading. Okay, we're not just loading textures, we're loading a bunch of them, we're loading 3D assets, very, very heavy. So you need to be very efficient when you load and display stuff. And JavaScript suffers from the fact it's not a language designed to be as fast as a machine could be. Okay, so it has good size and bad size, performance-wise. So what we wanted to do also is to be able to target, let's say, native platforms. So we can target native using native code. We think that embedding WebGL inside a web view is a bit cumbersome. It's really hard on the performances. It's really hard to debug and stuff. So be native where it can be native, like Android and iOS and Windows, etc. And be HTML5 in the browser. So what's inside Minko? The first thing is that we have today 2 languages supported. Basically, we have the core framework language, which is here to be fast, rich, and expressive. So as a developer who is building a massive library, you can have everything you need as a developer. And that can be optimized for each target. When I compile for iOS, I got optimizations for iOS precisely, for the precise architecture of the iOS CPUs. And you also have a scripting language which is simpler, which is interpreted, easier to work because you can just save your file and run the application again, no compile time, etc., and which is very dynamic. So inside Minko, we use C++11, which is not your daddy's C++, and I'll show you why. It's a standard, so it's already supported in all major compilers, so it works basically everywhere. And new additions make it really close from simpler languages like JavaScript. And that's what I'll show in a few slides. For the scripting side of things, we're using Lua. So if you think about it, it means we have Lua inside the Lua virtual machines, which is running inside JavaScript, which is itself running inside the virtual machines, which is running inside the web browser, which is a native application running on the operating system. But it's quite fast, you'll see in a minute. And the goal of Lua is to be able to have a very simple scripting language that you can learn actually in just half a day. So it's really simple language. And it's used in a large collection of games or commercial games like World of Warcraft, Fable, lots of games. So you get to choose between scripting and C++. So many features. So I think the most important thing is that it's free and open source. So it's 1 million lines of code of free and open source software on GitHub today. You have everything from GPU particles to 3D physics to plugins for Oculus and Leapmotion. I'll just show you a video, for example, of what we've done recently with Leapmotion. And once again, all of this is entirely cross-platform. So I'll show you a video of the Leapmotion, sorry. So this is running inside a native application, and just with one command line, okay, one push of a button, you have exactly the same app in your web browser without churning a single line of code. Okay? So here you can work on Windows, Mac, Linux, and HTML5 with the same source code. So we can even wrap up hardware like the Leapmotion or the Oculus Rift and make them entirely cross-platform very easily. So, ooh, green. Unity, I think today is one of the biggest, hottest platform to create games. So to compare Minko and Unity, they actually look a lot alike because you have a native core plus a virtual machines on top of them, and you write your application on top of that. So they're really, really similar. The big difference is that, again, we're fully open source, so you can do pretty much everything you want with the core framework and the plugins. We have lots of supported platforms, soon Windows Phone, because Microsoft has announced the new update for Windows Phone 8.1. As you can see, you can target also Linux server, which is pretty cool because you can do server-side rendering. So for example, if someone is accessing your app using an iPad and he doesn't have WebGL, you can do the rendering on the server side and have it displayed inside the browser. So as I said, Windows Phone is coming, Windows Phone 8.1. Windows Phone is a pretty good platform for games because more than 40% of the downloads on the Windows Store are games. So if you want to release a game on a platform, a mobile platform, Windows Store is actually a good platform to do it. So being able to target not just the web, but Windows Phone is a good thing. Something we have to, which you always need when you make a game, are parallelization. So you can have multiple threads and multiple workers working together. Again, all of this is entirely cross-platform. So I'll try to show you a little demo of what all of this means inside the browser. So I hope it will run properly. Okay. So this is on our website, minko.io, if you want to try it. Okay. Give it some time and come back later. And for the UI, you can build the UI using HTML5. So if you build native or web applications, you can use HTML5 on top of native 3D. So everything is entirely cross-platform, and you can use the best of HTML5 and the best of native code for each situation. So I think that's really great because when you build a mobile game, for example, you need to be responsive on the interface, on the user interface, because if you want to target the iPad or some Android devices, you need to be responsive, and HTML5 does that. So another big competitor for game development is Flash. Maybe you don't know about it, but Flash alone has more gamers than whole console game, gaming platform, gaming consoles combined together. So you add up Xbox One, Xbox 360, PS4, PS3, Wii U, Wii, all together, they still have less users than Flash has gamers. So it used to be, and it still is on the number, the best platform to build games. And what we'd like to provide today is a strict equivalent of what you have with Flash as far as tools are concerned, but only with open source, only with standard, only with free. Everything free and open. So people who ask Flash to be open source, there is no need. We've been doing something better, so just use it. So now to the hard thing, to the code itself. So I'll try to convince you that C++ is actually a cool language. Okay. So I've been training to do this with my girlfriend, for example, trying to explain to her the good things about C++, but she's not a developer, so didn't really work. But there are good things about C++, and especially about C++11. So what we have now in C++11 are called closures. So for a JavaScript developer, closure is a very basic thing. It's a function object. But when you're doing native code, it's actually very difficult to build closures. And here you have an example. You can read it even if you're not a C++ developer. Here, for example, I'm using the mouse. Okay, I have a mouse object, and I will listen to the. Okay. And I will attach to this signal a closure, which is just an inline function you see here that takes 3 parameters. and I will increment the distance, the zooming distance, according to this signal. So here, it's really not that far from how you would write it in JavaScript, okay? I think it's just as simple, but yet it's C++. The really good thing here is that using closures in C++ has no performance impact. So it's really easy to write, really cool to use, very simple to write your gaming logic, but it has zero impact on performance. That's a big difference between C++ and JavaScript. Okay, so basically same syntax or very close, but no impact on performances. So something very hard to do too with C++ is that you can manage memory as you want it. Inside the browser with JavaScript, you have to use the garbage collector. You don't have a choice. And sometimes when you build large-scale applications, it becomes a bit messy. So when you work with native languages, you handle the memory yourself. What happens when you have the liberty to work with the memory is that you make a mess. And you usually forget to free everything you allocate, and it makes everything crash, basically. So it's a two-sided gun. You think you can do whatever you want, but usually you do bad things. So what's really cool about C++11 is that you have something called share pointers, which is like automatic memory management. So when you allocate objects, when they're not used anymore, they will be collected. They're not garbage collected. They will be precisely deleted when they're not used anymore. Here you have a very good example for when you want to work with 3D. You will somehow allocate textures, for example. And when your texture is not useful anymore, you want it to be freed, both in your application and on the GPU. And thanks to share pointers, here what you see in the last 3 lines is that when I will set the value of my pp targets variable, the old value will be automatically deleted and freed, so I have some space available on my GPU and my CPU. And as a developer, I don't have to care about memory management, and yet it's very fast because there is no garbage collector. So I have really the best of both worlds. So that is just what's really good about C++11. So how can you take C++ code and bring it to the browser using Emscripten? I guess you've heard about it this morning, so I won't talk about it too much today. I think the most important thing about Emscripten is that it takes your C++ code and it turns it into JavaScript code, okay? And so everything you write runs inside the browser. So that's one thing, but how can you make sure that your C++ code will work properly on iOS, on Android, and on the web? Because you have to wrap everything correctly. So inside Minko, what we've done is that we've taken the work of Adobe, which has been working a lot on wrapping 3D interfaces for Flash. And we use the same system to wrap it using WebGL and OpenGL. So inside Minko, you have a class which is called an abstract context, which represents the 3D context you have on the screen, okay, how to display stuff. And that's abstract. So it could be DirectX, it could be OpenGL, it could be software, it could be a server, we don't know. And the only thing it does, it defines a set of interfaces that are used to render 3D stuff on the screen. Then you use the OpenGL ES2 context, which extends this class, and it will implement the context using OpenGL ES2. So it will work on Windows, iPhone, etc., on all native code. And then you think everything works well. The problem is that WebGL and OpenGL are not really the same. There are actually quite big differences that make WebGL perform a bit differently than OpenGL. So you have to do a new layer of abstraction, and you implement a WebGL context class that will behave like OpenGL, but modify a few stuff because WebGL is not really following the standards, okay? So that's how you abstract things inside your program to make sure that it will run everywhere, okay? And that's done for you inside Minko. You can do the same for DirectX, for example, if you want to target native DirectX. So now, how Emscripten works? I will not explain the inside of Emscripten, but I will explain what happens to your code when you want to target the web. So when you download Minko, you got a big repository, which is right here, okay? And you have here the core framework. Here you have lots of plugins, okay, like the bullet plugins for the physics, etc., etc. And one of the things you have are scripts to easily do some very complicated tasks. Like, for example, when I execute this, it will start compiling everything for HTML5. Okay? I don't have to install complicated things. I just execute a bash script, and it will start compiling my C++ code into HTML5. So for you, as a developer, it's magic when you use Minko. But actually, inside, it's doing very nasty stuff, and that's why I will explain in a few seconds. Okay, so if I just let it go, okay, and give him some CPU. Okay, that's not a good example. It's supposed to work. So you run some bad script, and it will compile everything for you in just a few minutes. Okay, so it's not as complicated as it might seem. So what's happened inside, what it's doing for you, is that it's using Emscripten to compile your code. So it takes your C++ code, and at the end, you have a JavaScript application. Not so fast. So what you have actually inside your application is that in blue, you have your source code, which is basically C++ code in the case of Minko. So you have the core framework, you have plugins, and all of this in separate projects, in separate libraries. We separate source files, we separate headers. It's a big mess of 1 million lines of code. And you have your application code, which is hopefully a bit smaller. And all of this got cross-compiled into asm.js JavaScript code. So each file will be converted one by one into an object JavaScript file. So for each C++ file, you got a JavaScript file. Then in the end, it takes all your JavaScript files, and it will combine them in one big application.js file, okay, where there is everything you need. And it's supposed to be runnable inside the browser. But there's a final step, and the final step is to take your application and optimize it. So it will run the Clojure compiler, for example. It will use LZDMA compression. It will optimize your code to have it a bit lighter, okay? So that's the part where I have to show Sponza. So let's see if it's loaded. Okay. So here you have an example. Okay, so that's a very famous 3D asset called Sponza. And as you can see, we have dynamic lighting. We have here particles. We have collision detection. Okay, that's the bullet physics engine. And the 3D model is loaded using asm, which is a C++ library, who can load a bit more than 50 different 3D file formats. So all of this cross-compiled inside the browser. Okay, the original 3D scene is 300 megabytes, and thanks to some compression and optimization, here in the browser is just around 7 megabytes. Okay, so here it runs in the browser, no plugin, no nothing. If you inspect this, and if my browser doesn't crash in the meantime, because it's a big JavaScript, you should be able to find the JavaScript somewhere. Oh, it's on the side, so let me show you. So it generates a big JavaScript. Okay, which is here, which is around 400 kilobytes here, so it's not that big, and it's compressed here. So it's when it's uncompressed, it must be around 3 megabytes. Okay, so you might think that it's a big file, 3 megabytes of JavaScript. Actually, when it's gzipped, it's a lot lighter. But keep in mind also that when you create a 3D game, you will likely load just one 3D asset that will be bigger than this. So the size of the framework is not really that much. Also, keep in mind that you have 1 million lines of code in just a few megabytes. That's really impressive. It's actually sometimes lighter than the native application itself. So Mozilla is really doing a good job when they generate the JavaScript. Okay, so that's just talking, just a demo. Now, how can you really use Minko to build a game? Okay, what's the real deal to build a game? So, how Minko works, the first thing is that we have a component-oriented framework. Usually when you use a 3D engine, you have like different scene nodes. You build a scene, and inside a scene, you have lights, you have cameras, you have meshes, you have all kinds of different objects in the scene to do all kinds of different things. And that's how we worked before, but it's not really extensible, because suppose you want to build a new component that will act like a mesh, okay, like a 3D object on the screen, but also like a light. It's actually very hard to do, okay? Because usually all those scene nodes classes inherit from another class and so forth, and you cannot have multiple inheritances without breaking everything in your code. So what we've done inside Minko is that the scene nodes are just nodes. It's just a tree, okay, just like any other tree. And how to make it behave like a light, for example, you add a light component. So you can easily have a node that behaves like a light, like a geometric shape, like a camera, etc., etc., etc. So there are two consequences. The first one is that you can create new components very easily, and you can combine them very easily. The second one is that you do not have to use components that are not interesting. For example, in all 3D scenes, usually we assume that every node of the scene has a 3D transform. That's not the case. Most of the time, all of the transform in a scene node are not doing any transformation, okay? So here you just add a transformation when you need it. So you win memory and you win some speed. So it's the same for camera. If you want a camera, you don't create a camera node. You create a node and you add a camera, which is pretty cool. So think about an FPS game. If you want to have the weapon and the camera, you can have them on the same node, and you animate just one node instead of a few nodes. So again, you get some speed and it takes less space. So that's for component-oriented and makes the framework a lot more extensible. Another cool thing is Lua coroutines. Something when you build application in the browser, which is very frustrating, is that the browser just stops. If you run a loop, the browser stops, okay? It's everything inside JavaScript. If you're not using the native browser asynchronous APIs, it just blocks the browser, okay? And that's very frustrating because when you build a game, you actually want to be free from those blocks. Just write your logic, okay? And let the browser make it asynchronous when it needs to be. That's something you can do very easily in Lua, and because now with Minko you can use Lua inside the browser, you can do it inside the browser. And it's called Lua coroutines. It's a very cool thing. Coroutines are like a function that can stop itself for an indeterminate time, and then resume when it should be resumed, okay? So think, for example, when you are scripting a character. You want your character, when it's idle, to say something funny, like, I don't know, I'm here to kick asses and chew bubblegum, and I'm out of bubblegum, okay, a classic one. So you want to say something funny every 3 seconds. If you do it with JavaScript, you create a timer and wait for 3 seconds and say something new, etc., etc. You have lots of functions and handlers everywhere. Here, with coroutines, you can just do an infinite loop, yes, infinite, that will just say something and wait for 3 seconds and just do the next iteration. And it will not block the browser. So everything is a lot easier to write. So here, for example, you have an infinite loop that will just say, hello, how are you, every 3 seconds. And here you have an infinite loop that will just wait for the keyboard to be pressed to do something, okay? And all of this is just exactly, this is not pseudocode, this is actual code. So when I say Lua is very simple, it's actually very, very simple. So it's really simple to build application scripts. So now real use case. Okay, so I'm amazing at game design. Okay, that's a given. That's a very simple football game. And now we'll explain how you build such a game with Minko. Okay, so maybe you don't see it, but on the top left corner, you have the score. So every time the ball actually falls on the one side or the other, the score is incremented. So you have 2 for the blue right now, or 1, 2, I don't know, too small. So I'm not just good at game design, I'm also good at UI design. So that's a very simple game, okay? So how can you build this game very easily and make it run in the browser? So this is what you get inside Minko Studio, so you open the editor. You might think you'll do this with code. I will start without a single line of code, okay? Nothing. So just open Minko Studio, and what you see on the left of the screen is our 3D scene, okay? So you have a very quick lookup on everything you have in the scene, and here you have our yellow cube, our green sphere, which is our ball, and our global setup. And now I will explain how we can make this interactive very easily. So the first step is to handle some physics. And to do this, I will zoom in here. Okay. On the right, you can say that our box, which is here, is a collider. Okay. Or for example, the ground of the game is a collider, or the walls here. So just add a collider, and if you are designing the walls, you make it static because it must not move, okay? The ground will not be influenced by gravity. Actually, it is, but not in this game, okay? So that's the first step. Have your global stadium, football stadium ready. Then you'll do pretty much the same for the ball here, so the ball, for the player, sorry, my handsome player. And you will say it's a box collider, okay? But it's not static because it's moving, okay? It's our player. And you will do the same for the ball, and you will say it's a collider. And instead of being a box, it's a ball, okay? Different physics model, but same idea. So the final result, when you do it with actual graphics, is something like this. So here I'm opening Minko Studio, which is our 3D editor, to show you an actual football stadium built on the exact same principle. Okay? So everything you see in blue, okay, the blue stuff all around, are colliders, okay? So virtual walls, virtual physics walls. You'll notice that we have colliders all around the stadium, and here around the goals themselves, okay? And we have a collider for the ground too. I can show everything here. Okay, so for example, we have a collider for the ground, which is here, okay, right there. And we have a collider for each walls. Okay, that's a north wall, etc., etc., etc. Okay? Everything is done inside the editor. So when you load these 3D assets, okay, the physics is already on it, and I just have one line of code to load it, and it runs with the physics inside my browser. Okay, so directly from 3ds Max to my browser through this 3D editor. So then comes the interactive part, because this is a 3D asset with physics. How do you make it a game? It's a football game. So the next thing we have to do is to make sure that we detect when the ball hits the goal. So you're a developer. Your first reflex is to say, okay, I have to detect when the ball actually enters the goals. Simple. So how would you do it? Well, it's a very simple thing. You can maybe check if the ball is beyond some limit. There are multiple ways to do it, but a very simple way to do it is to use physics. So for example, here, inside my first goal, I have a collider, okay, which is inside the goal. You can see here in blue. And you think it's pretty stupid because I have a collider inside the goal, so the ball cannot go inside, okay? It's blocked by the collider. But it's a special collider. It's what we call a trigger, okay? A trigger is just a collider, and I just check the trigger box. And it will behave differently. Instead of colliding with stuff, it will tell you when it collides, okay? It will not be a constraint. It will just tell you, hey, I'm colliding with something, okay? For example, it will tell you, hey, I'm colliding with the ball. So in your code, you just have to do a little script that will tell you, hey, this goal is colliding with the goal, so you score. And you do the exact same thing for the other goal on the other side. You have another trigger, okay, which is right here. And you just use the same script, but increment a different score. Okay? So this is how, inside the editor, most of the game logic is laid out and how you can use physics to detect a lot of things. For example, think about when your player is closing on a door and you want the door to open automatically. It's actually a pretty difficult thing to do, and if you have hundreds of doors in the level, it's actually pretty hard to do it efficiently. But if you use this system, you rely on the fact that physics is really fast, something to bullet, and you can detect when someone enters an area, play a script, run some dialogue, etc., very easily. Okay? Of course, you do the same with the players. So here, for example, you have Ninja. Okay? And what's really interesting, so you have the colliders around the Ninja because it's supposed to, of course, collide with the ball or with other players, for example. If I press play, you see the physics running. Okay? So much that if I start an empty scene and create a cube, for example, I'll just copy-paste it. I will make it a bit bigger. Okay. I will add some light. Okay. So I have my scene shaded. Very simple. I had some ambient lighting. Okay, much better. Okay. If I press play, there's no physics, nothing happened. If I add the collider here, I press play, physics happen. I don't want it to fall, so I make it static, just like with my stadium, and it stays right where it's supposed to stay. I add collider here, and boom. Okay, so I can really test and run my physics and my animations inside the editor. So I think the really good thing is that you don't need to be a developer to do this. So your artists, your game designers can do it, and it's really a lot faster. And then when you're inside the game, all of this works exactly the same as inside the editor, or it's supposed to. That's not a good day for demos. Okay, so you get the idea. So now I'll show you the final result. Okay. So here is what you get. So the thing you see here, so the UI is done using HTML5. So this game runs on Windows, Mac, Linux, iOS, Android, and HTML5. And the UI is done on HTML5. And it works the same on all contexts. You see our players, you see some nice particles effects here. And you see the ball. All of this is entirely based on physics and some scripts. So the whole game must be like 2,000 lines of code. Very simple application. And yet it's a complete game that works everywhere. Okay? So that's a game we've built using Flash a few months ago. And we built it in only 2 days. Okay? That's 2 days of work. Or actually, that's 48 hours with 10 people. So that's not 2 days, not 2 man days, but just you start the Friday and you are finished the Sunday. And we're building the exact same game using only C++ and JavaScript. And today it's taking a bit longer, so it's taking like 5 or 7 days. But I'm guessing that if you were to do this with no tools at all, it would take even more time. Okay, so I'm not talking about particles, but they're also a very important part of the game. So inside the editor, if you want to create some particles, I'll just show you an example. So okay, so for example, those are particles that are played when a player spawns on the field. If I had to do this with code, I wouldn't know how to start. You can do this with the particles API, but it takes so much time to make trials and errors. And I think the biggest problem is that I'm a developer, I'm not a designer, so I want the designer to do this. Okay? And if you don't give designers some tools, they'll never be able to do it, okay? But here they can just use the editor and can just modify everything they want to change the shape of the emitter, to change the colors of the particles, or not. I'm cursed. So you can change everything. For example, I want a lot more particle. More particles. Okay. Just for the fun of it. It's over 9,000. Okay. Okay. 9,000 particles. And it runs the same on all platforms. Okay. So, my conclusion. So, working with C++11 is pretty great. I've done JavaScript, I've done ActionScript, and I won't go back. It's true that it's a much more complex language, but if you go on all game dev forums, you'll see that if you ask what is the best language to develop a game today, most people will answer C++. And I think C++ is a major step to do this even easier. I think that working with Visual Studio or Xcode is a game changer. So imagine that you have just the best development tools. I'm not saying this because we are at Microsoft, okay? But it's a given that Visual Studio, okay, doesn't have any match on Linux. That's a fact. That Xcode is a good challenger for Visual Studio, but it's a very good tool to create application. You have a good debugger, good profiler, so it's really, really amazing. And to me, it's a lot better than everything we have in JavaScript today. So it's really, really important. So we've done everything from ActionScript to C++, and now we've managed to make things simpler instead of more complex, so we're pretty happy. And using some nice tools like Vagrant and Premake, it's actually pretty easy to build a C++ on all platforms. So surprisingly, it works everywhere. When it was running inside the browser, it just took half a day to have C++ code running inside the browser and display a rotating cube, okay? It was like 8 months ago. Now we have so many things working inside the browser, but the tools are really mature, I would say. The size of the applications are actually quite good because you would expect them to be like tens of megabytes, and usually they're not. And the speed is amazing because you have close to native speed. So what you do when you write C++ for the browser is you have really much more higher performances than what you have when you write a JavaScript code by hand. You could match this speed by hand, okay, by doing asm.js optimization yourself, but it takes a lot of time and your code is not readable. So using a C++ and Emscripten, you have readable code and the best performances inside the browser, and I think that's really awesome. Integration Emscripten is a really great tool, okay? It's really new, but it works really well, so we're really surprised. The bad parts, okay, so today it's pretty hard to build dynamic libraries, so I don't know how to do it. Today WebGL is too slow. So really, really, really slow. If you compare WebGL to its competitor in Flash, for example, it's really like between 5 and 7 times slower. So I think all the browsers need to step up and have better implementations for WebGL. And I think that will be really the game changer for the future of gaming in the browser, better performances for WebGL. When you write C++ for the browser, it will also eat up a lot more memory. So be ready for this. It's getting better and better, but really sometimes it seems excessive. Some numbers to close up. So I'd said 1 million lines of code, free, open source. 70 support for file formats for Minko. So some people ask, do you handle that file format? Yes, okay, no matter what it is, I think we handle it. We use 20 different open source projects, so if you're an open source fan, I think this is open source porn, okay? So just go grab it. We support 6 different platforms, around 20 different architectures. When we compile the SDK for all platforms, it's 20 gigabytes, okay? It's a big, fat SDK. Hopefully you don't have to download those 20 gigabytes, but just to tell you how big it is, as a binary. There are more than 50 tutorials, so if you want to get started, you can get started with 50 tutorials, 10 example projects, and 17 plugins to handle Oculus Rift, Leap Motion, and stuff like this. We don't have a buzzer thing, but it's coming next release, I hope, with OpenAL. Okay, so C++11 is Go for games, and Emscripten, which was presented in more depth by Mozilla, is, I think, a very mature solution to build native game for the browser. So merci. Don't forget to check minko.io. The new website is online. Okay, it was put online like 4 hours ago, and everything I've shown is, again, open and free on GitHub. Questions?
So, do you have question? Yes.
Hello. Well,
Hi.
first I would like to congratulate you because the demo was really impressive.
Thank you.
So that's really great. I have a question though. So in the previous presentation about Babylon.js, said they were implementing cache support for the web. So I would like to know if you have something to deal with cache in Minko.
To do with cache?
Yeah.
You mean caching the JavaScript or the assets?
The assets, mainly.
So loading through the assets is a big problem that we have on the web, but not on consoles or PC gaming, for example, because the bandwidth of the web is a lot smaller than the bandwidth we have with hard drives or Blu-ray, etc. It's orders of magnitude slower. So that's why we're developing compression and streaming algorithms specifically for 3D meshes. So that speeds up 3D meshes loading by, in the best case, is a factor of 200. So that's the first thing. Then caching. For now, we are relying a lot on Emscripten, which has a virtual file system thing. And I'm guessing that that's rather their job to implement caching system in the browser rather than ours job. But that's something interesting because that's something you definitely need. But I think that caching is okay when you've started the game and played once. If you look at the stats, after just 10 or 20 seconds, you lose half of your audience because it takes too much time to load. So right now we're focusing on the first launch experience, which is pretty bad in most cases. And cache is always cool for the next time you come by.
Other question?
So this is not exactly on Minko itself, but it's more on the pipeline that you described. Write code in C++ and then convert it to JavaScript. So if you have some code that's using threads on your native side, what happens to that when you convert it into JavaScript, for example?
Code which is using?
Emscripten.
Okay, so I'm not sure I understand the question.
Threads. Let's say you're using threads, multi-threading on
okay, threads. So you don't have threads inside the browser. So there are nice attempts. Adobe has a similar tool than Emscripten, which is called Crossbridge, which similarly compiles C++ to ActionScript 3. And they have a threading emulation pipeline which use workers and shared memory to simulate some userland threads. So you should be able to do this with Emscripten too. It's not done today, but as the pipeline is pretty much the same and the workflow is pretty much the same, it could be done. So today, the only thing you have inside the browser to do threading-like stuff are coroutines in Lua, which is just a thread emulation in some way, and you have workers. And so what we provide is a worker API. So when you create a worker, it will work seamlessly in JavaScript or in threads inside your native code. So threads in native code, workers in the browser. But for you as a user, we provide the wrapper. Okay, so it's doable.
More question? No? Yes, one.
Sorry, I don't remember the name of the asset. You know, the big Coliseum, not the Coliseum.
Yep.
How many FPS do you have on this one?
On this, 60, because it's a very simple 3D asset, actually. It's just, I can show you the exact.
No, not this one. You know the Coliseum.
Sponza.
Sponza, yes.
I don't have a FPS meter on it, so I don't know. But we're using the interframe of the browser, so we have how many frames as we can. Just let me load it. Most of the time you get 60 frames per second. So.
Okay.
Here the bottleneck is WebGL because we have lots of 3D objects, too many of them. But
in fact, that was my second question. You claim that WebGL is a slowdown, it's slower than Flash. Do you have any bench?
I don't have bench in my slides, but I can do bench because we have the same applications running in Minko 3, which is C++ running through asm.js, and Minko 2, which is Flash. And the thing is that Flash is really crappy at emulating the differences between OpenGL and DirectX. So they provide a very low-level API, and this very low-level API makes it easier to manage memory between the CPU and the GPU, and that's what creates a big performance gap between Flash and WebGL today. If you go on a website and profile this in your browser, you'll see that all the functions that use a CPU are WebGL functions. So you don't see bullets, you don't see file loading, you see really the WebGL stuff. And that's because Flash is, in the end, so crappy at abstracting properly DirectX and OpenGL that you have more freedom in the memory management. And that's one of the biggest differences.
On the WebGL performance side of things, I know that a lot of the performance difference that happened between WebGL and like raw OpenGL currently is because of how browsers do compositing, and this is an area where Gecko is changing a lot, especially in Windows. Like new stuff is gonna arrive soon. So basically, what happens is that you have synchronization points between the CPU and the GPU, and then suddenly you need to flush your entire command queue when you want to go to the screen. And there is work into making this more synchronous, and I guess other browsers have the same thing. It's just like the architecture of web browsers is kind of evolving quite rapidly, and
I'm sure
we're moving to something that is
and it was not a complaint, just
no, I'm just like to reassure you, it's coming.
Okay, great. Okay, it's actually a very complex thing to solve, and we intend to close the gap because we can do some things on our end. To explain a bit further on ActionScript, we had our own shader compiler, which was much more, which was better at generating good bytecode, and we could have our own memory layout for our shaders, which was just one big byte array. So when we have to upload things between the CPU and GPU, it's just one operation. And when you do it with OpenGL, you have to do a lot of uniform setting. And we have to do a lot of work to optimize shaders and pack uniforms automatically, etc., etc. And that's something that we have to do, that the Unreal Engine is doing, for example, if you read the Unreal Engine shaders. But that's something that is proprietary, and we have to redo it in open source. So if you're interested in the subject.
Okay, thanks.